All right. Can everyone hear me well? Okay, cool. Thanks. All right, welcome to lecture 23A. Today we'll talk about memory organization and technology, especially about DRAM organization and some details about how we operate our DRAM chips today. And we'll look at DRAM-based main memory. In the last lecture, we covered some memory motivation content, right? I motivated memory, why it's important. And I'll start with a review of those. Basically, memory is critical for computing. And it's critical for computing because of it affects multiple system performance metrics. Here, the first bullet you see performance is typically expressed as system throughput or latency, right? How fast can you do computation? But there are other performance metrics that we're interested in equally. These can be equally important based on what sort of a system you're developing. And memory design will affect all of these performance metrics, basically. We talked about ideal memory. This ideal memory would have zero access time, zero latency, infinite capacity, zero cost, infinite bandwidth, and zero energy cost per access. But it's very difficult to have the best of all characteristics. And even two requirements will oppose each other. The most simple example I can give here, and you will probably understand based on what we covered, is latency and density, right? The larger your memory array gets, the slower you access it. And that's a fundamental trade-off because your wires become longer, and then it takes more time to develop a reliable signal on those wires. We looked at how we can store data today. We covered a bunch of different technologies, but we looked at what they excel at and what they're bad at, and then hopefully you remember simplified array organization of memory. We will look at this array organization in more detail today in the context of DRAM. And to build larger memories, we require larger memory arrays. But because large is slow, we will basically divide our large memory array into smaller memory arrays. And you will see examples of this. And these will be hierarchical structures. For DRAM specifically, the hierarchical organization looks like this. You have a channel, then a rank, bank, some subarrays, and mats. Here's another view of that hierarchical structure. I'm going a bit fast because we covered this in the last lecture. I'll start from the rightmost side again. You can see I cannot see my pointer, just a second. Okay. You can see my pointer here. So in the rightmost side, we have this DRAM array structure formed of columns and rows. This 2D array of DRAM cells will form a bank. And you will have multiple banks in a DRAM chip. And a DRAM chip is basically multiple DRAM chips will form what we call a DRAM rank. And then this is connected to the memory controller or your processor chip over a memory channel. And in the end, your performance is bottlenecked by how much load you have on each channel. And this is like another view of the same structure. Here you can see what the channel is composed of in more detail, right? You have a command bus. You use this to send the DRAM chip some commands. We will talk about those later. And the address bus, obviously, you need to send an address if you want to read some memory location. You need to send the address that you want to read from. And the data bus is usually two-directional. So basically, you'll use the same signal to convey data from the memory chip to the processor chip and the processor chip to the memory chip. And this is to minimize cost. These ranks here and ranks, the chips in a rank and the banks in a chip will share command address and data buses to, I would say, again, minimize cost, but we will dive into that more a little later. And I'll just make another remark here. You cannot have a ton of memory channels to improve your system throughput or memory parallelism because each connection will cost you some pins. And pins are very expensive. You cannot very easily have 1 million pins. And because these will go outside the package over the PCB in a system where you have different electrical characteristics to basically satisfy. It becomes difficult. And they require a lot of area in your processor chip as well. The more pins you add, the more area you need to control this memory chip. But if you're making connections, these pin connections inside a chip, like in a single chip or on top of a chip, by using 3D stacking technology, you can have more memory channels implemented essentially. And that allows you to get higher throughput access to your memory. And this is an example, 3D stacked memory technology. I think there are other 3D stack technology developed, like other 3D stack technologies being developed today, but we won't go into details about those. Now, okay, we will take a top-down view at the DRAM subsystem. Why DRAM? Because we use it prominently in almost all computing systems today, typically as main memory. And the DRAM subsystem organization will look like this. It will have this sort of hierarchy, starting at the top, or starting from the processor side, you have channels, and then you will have DIMMs. These are dual inline memory modules. You don't need to know what they mean, what that means. And then ranks, chips, banks, rows, and columns. So this is a pictorial view of the same thing. You have a processor here in the middle, 2 memory channels in this system. And inside one channel, you can have multiple modules placed. And this is what we mean by this module that you see here, what we mean by a dual inline memory module. And yeah, as you can see, today's processor can have multiple channels. This is what a module looks like. So it can have chips on either side. And you can see the front side of the DIMM, back side of the DIMM illustrated here, right? Now these typically on one side of the chip, on one side of the module, you will have one rank of chips. Why do we have this rank sort of naming here? Because they share the command and address buses as well as data buses. So if you want to send a command or if you want to read data from a rank, you have to send that address and the corresponding command with this in this shared bus. Both ranks will receive that command and address, but you have this additional signal called chip select. It actually selects a rank of chips. It's kind of misleading, the naming, but this is how it's named in the standard if you look at it. I was very confused when I was getting into memory in the first time. But this, you can basically select which rank will operate on this command that you sent by selecting the corresponding chip select signal. And that means basically these ranks sort of time share this address and command buses, as well as the data bus. And you need a means of selecting which rank will output data on the data bus, and conceptually that's done via a multiplexer. What's inside a rank? You will have multiple chips. You will have 64 bits of data coming to your rank of chips, but these are distributed to, in this example, 8 different chips. And each chip here receives 8 bits of data. Why do we have this sort of a connection? Because pins, again, are costly. Each chip you have here is pin limited, and you distribute the data pins to the modules to chips like such. And this is because basically memory is today memory is very cost optimized. It's considered a commodity basically, and the designers and engineers and manufacturers try to optimize cost as much as they can. Okay, so this is what's inside a chip. You have multiple banks. You have 8 bits of data coming to your chip, and all 8 banks can provide 8 bits of data. But if you remember, we have these banks so that we can leverage what we call bank level parallelism. I'll try to describe that over an example just to remind you. Basically, you will have long latency access to each bank, right? Your access to a bank might take 16 nanoseconds, for example. But in the consecutive cycle, after starting the first access, you can start an access to another bank. And that way you can overlap the latency of accessing multiple banks. And in this example, basically, you can send one command to this first bank to retrieve 8 bits at some point in the future. And then immediately after, in the next cycle, you can send the same command to another bank. And then you will receive the read data in consecutive cycles as well in the future. So what's inside a bank? Now, this is the two-dimensional array structure we have seen before. We have what we call columns of DRAM cells. This is typically 1 byte. That means 8 cells make up a column. And you have multiple rows, many rows actually. In this example, you have 32,000 rows, but in the latest standard DDR, well, for example, one of the latest standards, DDR5, you can go, I think, up to 256,000 rows in one chip. That might be wrong. It could be 128 as well, but it's not so important. You have what's called a row buffer. This is, we didn't describe these structures yet, but this is an array of sense amplifiers that you have to go through to access data residing in your DRAM cells. I'll talk about it in more detail later. And from this row buffer, you have connections to the chip interface. So you basically, we will see in the next slide how you operate this array. But the basic idea is you retrieve the row of whatever's contained in a row of cells to this structure called row buffer first. And then from the row buffer, you can send your read and write commands. And this example will explain it better, help me explain it better to you. This view is obviously an abstraction of a bank. We will see how actually a bank looks like more in the upcoming slides. So the hierarchy didn't end yet. And internally, a bank consists of many cells. Each cell, if you remember, is a transistor and a capacitor, and other structures that enable access to this cells, like row buffer. We will put the row buffer here separately. It's an array of sense amplifiers. Initially, it's empty. So we will access this address, row 0, column 0. And for that, we need to provide a row address to the row decoder. And the row decoder will enable what we call a word line that corresponds to the address of the row. And then you will have brought row 0 to the row buffers with at the end of this access. Now you can send a read command to column 0. And then that will select the corresponding address in the row buffer that corresponds to row 0 and put it through the column multiplexer and output it to your data pins. Now, what happens if we access another column? This is kind of interesting because now we have the data already in the row buffer. We don't have to bring data from the DRAM array to the row buffer. We can just serve this request. This is also called a row buffer hit because you found the data in the row buffer, the data you want to access in the row buffer. So you can serve this data, this request much faster, and you will just put the data through the column mux to your data pins. And if another access comes to another column in the same row, you again just serve the request from the row buffer. This happens fast. Now, what happens when you want to access another row? To keep it simple, I will just say that you have to reset the state of the array to an initial state that will allow you to access, retrieve a row of data to the sense amplifiers, and that takes time. So you'll do that. This is also called, this access at this point will be called, we call it a row buffer conflict because you have to bring another row to the row buffer. You have to reset the internal state, as I mentioned. And this will take some time. Now you can put the new address to your row decoder circuitry that will enable a different word line, and that will bring row 1 to the row buffers. And now you can finally serve the read request by bringing the data that corresponds to column 0 in row 1. So row buffer hits take less time, row conflicts take more time, and interestingly, memory controllers inside their processor chips will try to optimize row buffer hits over row buffer conflicts. What do I mean by that? If you have a bunch of requests in your request queue in the memory controller, you try to prioritize requests that hit in the row buffer over requests that would cause row buffer conflict. But that's a whole, I would say, even research area, because if you do that, then you might end up accidentally prioritizing some workloads over others because they keep getting row buffer hits, and you deprioritize workloads that have row buffer conflicts, and that causes fairness issues in your system. But we won't get to the details into that in this course. If you're interested in that, I suggest you take the the master's course, computer architecture course that we give. Okay, so this is how you operate your DRAM bank at a high level. Do you have any questions? I see a hand over there. Yes. How do we refresh? Okay, that's a good question. So the question is, how do we refresh data? And this refers to DRAM cells being leaky and losing charge over time. Basically, to do a refresh operation at this level of abstraction, I could tell you that if you need to refresh row 0, for example, the only thing you need to do is to activate row 0 by putting that row 0's address to the row decoder. That will bring the data to the sense amplifiers. And because of how the sort of memory array operates, we will get to that in upcoming slides in more detail. But because of how the memory array operates, the moment you bring data to the sense amplifiers, you've actually also restored the charge in the capacitors of the row. So by accessing a row, you have refreshed it, essentially. There was...
Why exactly is, if we go to column 85, why is it different? Because it's still in the same row, I don't know.
Yes. So the question is, why is row 0 column 85? This access causes a row conflict. It doesn't. Maybe I made a mistake in explaining it to you. Yeah, it's a row. Oh, it's a row hit because your row is still 0. Yeah.
So only the next one is.
Yeah. Mm-hmm.
Because we can access different banks in consecutive cycles. But now when we have, for example, in our second request, so one request, and the next cycle another request, and the second request has a hit. How is it managed that now not, because like the second request returns faster because we have a hit. Now it couldn't happen that those charge right back simultaneously, and then we have a data conflict.
Yes, it's a great observation. So I will try to summarize your question. We have multiple banks, and we can start accesses in those multiple banks in consecutive cycles. But I've shown you here that so 2 consecutive requests, you can serve from the same bank in consecutive cycles, right? Basically, you don't have bandwidth to serve another request that could go to a different bank. And at that point, you have to, as the memory controller, you have to make a decision. You need to either serve one request or do the other. Fortunately, you can send a lot of commands between 2 read requests to the same bank. Basically, what you could do, you cannot read from 2 different banks, in this case, in consecutive cycles, but you could still start an access in a different bank. You cannot overlap the portion of the operation where you have to send data out through the data pins, but you can still activate a row in a different bank between 2 read requests, 2 read commands. Yeah, this is a good question. Yeah, thanks. I don't see any other hands, but please shout if you want to ask a question. I cannot see your hands. Okay. Yeah, we've covered this. What happens? What's inside a bank? We won't look at DRAM operation at this much detail, but we will look at how it's organized further. You have what's called subarrays, or also named subbanks, inside a bank. You're partitioning your array further and further, basically. This left picture here is from the perspective of the memory controller. This is a logical abstraction of a bank. And the right picture shows you what it actually looks like. And here you can see the key idea of this sort of an organization is your distance in an arbitrary cell in one subarray to the local row buffer or the sense amplifier is shorter than what you would have in the logical abstraction view. Basically, we have made the cables that connect DRAM cells to sense amplifiers shorter, and that allows faster access. And the key takeaway from this slide, I guess, is you divide your array into smaller and smaller arrays to keep your latencies small. Now, you might have thought that the hierarchy ends there, but you also have what's called mats. We won't cover these in detail, but I promise mats are where the recursion ends for now. Why do you have these? Now, I can find two reasons why you have these. But again, it's in the line, it follows the line of thinking that we have smaller arrays and faster, or smaller arrays and smaller latencies, right? You simplify the connection between sense amplifiers here and the global bit lines. So what are global bit lines? You have seen row buffer already. You have to take data out from the row buffer to the chip interface. Before that, basically in between that, on that path, you have what's called global sense amplifiers. These are smaller. These are still operating similarly to your row buffers. Smaller in the sense that you have fewer of these. You connect some of the sense amplifiers with each read access to your global sense amplifiers. And this mat organization will allow you to shorten the distance between any sense amplifier and a global sense amplifier connection, which is labeled as global bit line here. The other reason you have mats, you have shorter word lines. Word lines go in this direction, you can see, and these have become shorter with this organization now. So again, you shrink your array, you get faster access. Okay. If you're interested in DRAM basics and organization, there's more in this papers. You can see section 2 for a comprehensive DRAM background, more comprehensive than what we've covered in this lecture. And with that, DRAM subsystem organization is complete. But before we move on, we will look at also an example where we transfer a cache block from our processor or from our system to main memory. What's a cache block? This is basically the granularity of data that you transfer between your main memory and your processor system today. It can be 500. It's typically 512 bits. That's why we have it 512 bits here, but it could be different. And why are cache blocks 64 bytes or 512 bits in this example? The basic idea is, okay, let me mention this first. You have seen processor load store instructions. They're usually in the granularities of words, bytes, half words, double words. Like basically they go from 1 byte to 8 bytes. So even though the processor accesses data in at most 8-byte granularity, why do we have 64-byte cache lines? This will become more clear in the caches lecture, but the basic idea is with a single access, you retrieve more than, let's say, 8 bytes. Your processor wants to access 8 bytes. You retrieve from the start address of that request the next 64 bytes. Now, if the processor happens to access the next 8 bytes, you have it ready in your caches. This is what we call spatial locality, and this larger cache block size allows you to exploit spatial locality in your processors. I'll leave it at that, but the caches lecture will give you more insight. Here we will see how we map this cache block here, the first cache block in our physical memory space, to one module in our memory subsystem. So this is another view of this module we have. In one rank, we have 8 chips in this example. And the data pins, there are 64 data pins. And each chip gets 8 data pins. We have a 64-byte cache block, but we have only 64 data pins. That means a 64-bit bus. And you can already figure out this transfer will happen over multiple cycles, right? Multiple data bus or DRAM bus cycles. So how do we place this data? One cache block, 8 bytes of a cache block will be spread across 8 chips. So each chip will receive 1 byte in each clock cycle. This clock cycle is from the perspective of the DRAM bus. So each chip receives 1 byte. That is 8 bytes transferred in a single cycle. And you can put these bytes in, starting from column 0 in one row, and the next byte to row 1. And basically, you just place one byte to, like every byte to consecutive columns. Right? You can see where this is going. I hope it's not too unclear. We refer to this operation, data transfer burst. Basically, you send a single read command, but you receive data in a burst of 8 data transfers in this example. Why does this happen? Because you couldn't have a larger bus to do this operation in a single cycle, because you are pin limited, pins are expensive. But why don't you send one read command for each 8 byte transfer? That basically, if you had that, you would be utilizing the command bus too much for, I wouldn't say no reason, but because we expect to transfer data in cache block granularity, you don't really need to have reads that would get you 8 bytes only. You can have one read and receive 64 bytes. Compared to the case where you have reads retrieving 8 bytes, you have more opportunity to send other commands in the DRAM command bus. Because previously you would send 8 read commands, now you send one read command. The data bus is utilized, sending that data over 8 cycles, but you can send other commands like to activate a row in another bank until you receive that data. Does that make sense? I don't have content in the slides to back that up, but I want to explain it regardless. Okay. Any questions so far? We're gonna shift gears. I would say shift gears down. We're gonna slow down and finish this part of the lecture soon. I'll give you a quick overview of the underlying technology for DRAM and a bit of SRAM. So we'll start with DRAM. This is dynamic. This is also called, well, the longer version. The long name is dynamic random access memory. Why is it called dynamic? Because you lose the data that you put in your DRAM cell over time. So you store data as charge in a capacitor, and whether or not this is charged, the cell is charged, indicates the stored value. So if you could encode data in this way, for example, if the cell is charged, if the capacitor is charged, that's a logic 1. If the capacitor is discharged, it's a logic 0. You have one capacitor, one access transistor that connects the capacitor to the bit line, and this access transistor is controlled via the word line. And this capacitor will leak charge over time, and that's why it loses data through the resistance path, through the resistor capacitor path, and it will lose charge over time, and you need to refresh the charge that's lost. So I'll give you some more insights into the analog operation of how you access a DRAM cell, but it's not going to be too much. This is a diagram showing you how you connect a DRAM cell here at the capacitor to a sense amplifier. And the cell has 2 components. You know that word line controls the access transistor, bit line connects the cell to the sense amplifier. There's also a bit line bar that we're not so much interested in. And there's also an enable signal that enables the sense amplifier, which means the sense amplifier will amplify the voltage difference it sees, and the bit line, the voltage difference in bit line and bit line bar. That's basically when you copy data from a row to your row buffer. Okay, initially, both the access transistor and the sense amplifier here are disabled, and both ends of the sense amplifier are driven to half VDD. So VDD, we use it to indicate the charge state, let's say. That means you encode a value of 1 in your cell. It has a VDD voltage, we call it. And to access this cell, you first enable the word line, and this will connect the capacitor to the bit line. And what happens then? Since the capacitor had a voltage level that's higher than the bit line, right? It had VDD voltage, but the bit line is only half VDD. It will leak or share its charge with the bit line. And this will deviate the bit line voltage towards VDD. This becomes half VDD plus epsilon, or whatever that is. And then you enable the sense amplifier. When you enable it, it will compare the voltage levels of bit line and bit line bar. You can see that the bit line bar here is already half VDD, and bit line is above half VDD. So the direction of, let's say, charge or voltage will go in this direction. So you will set bit line to VDD, and then bit line bar will be 0, but that's not important for our example. Now you can also see that the word line is still enabled. So the capacitor is already connected to the bit line, but bit line has VDD, voltage has a voltage level of VDD. So this will also restore the lost charge back to the capacitor. So this is what I meant when I tried to explain, like when you access a DRAM cell, you also restore charge back to it due to how your device operates. Okay. This is just some detail, not too much. Now we'll talk about SRAM a bit. Do you have any questions so far? No. Okay. You have two cross-couple inverters to store a single bit. You have this feedback path here between these two cross-couple inverters that will allow the value to stay in the cell as long as there's power. You have 4 transistors for storage, 4 transistors because each inverter here requires 2, and then 2 transistors for access. You connect the single cell to both bit lines, two bit lines here, and that allows differential sensing and, well, I will say just low latency differential sensing. So this performs. I will say that this performs better than DRAM in terms of latency. What sort of memory bank organization you have? It's similar to what we have seen. So I will just cover this very quickly. There's nothing new to see here. It's very similar to what we have seen in DRAM. And the main difference between an SRAM array and DRAM array is basically SRAM resides in processor chips, so you have more opportunity to add wires, and that will give you this will provide you with the possibility to perform or provide row and column addresses to your array structure in the same clock cycle, whereas you won't have that in DRAM, and we'll see it in the next slide. So basically in DRAM you have what you call a row access strobe or RAS. This will you will provide your row address in one cycle, and you will store that here in this. Let's say this is a latch or a register, and in another cycle you can, using the same signals, you need to provide a column address. So first you make your row address, you bring data to the row buffer, and then it has to happen in a consecutive cycle or some cycles later. You will provide which column you want the data from. This is because you don't have the same opportunity of having plenty of wires in a DRAM chip. So we will leave this at that. And finally, I'll maybe go over the slide very quickly. I will compare DRAM to SRAM qualitatively at a high level. DRAM compared to SRAM has slower access. This is due to how the technology basically. Your capacitor operates fundamentally slower compared to that back-to-back inverter, whereas SRAM is faster. DRAM, you can have higher density because you have 1 transistor and 1 capacitor, whereas you have 6 transistors in an SRAM cell. It can be less or more than 6 transistors. We've covered that. But in general, a DRAM cell takes up much less area to implement than an SRAM cell. You have lower cost for DRAM because you can implement more cells per chip area, I would say. And DRAM requires refresh, so that gives you some extra power overhead, because performing a refresh operation requires you to open a row that has thousands of cells and write data back, right? And finally, manufacturing requires, for DRAM's case, putting capacitor and logic together. What does this mean? Because basically, you have a DRAM array that's subject to interesting manufacturing constraints. and you have to put some logic around it to have the access array access path implemented. You have some logic elements basically inside the DRAM chip, outside the DRAM array. And this makes it a bit more challenging to manufacture. Whereas SRAM, well, you have it compatible with logic process already. You can put SRAM in your processor chips. We know how to do that well as humanity, I guess. There's no, well, there are challenges, there are manufacturing challenges there, especially with scaling, but compared to DRAM, you're not challenged additionally, let's say. Okay, just a few more slides left. So we've covered the most important bulk of this lecture. Now I'll show you some slides. These will talk about, I just want to talk about some emerging and other memory technologies that we did not cover. And I'll have some pointers to relevant research papers and some talks that we have given in the past and other resources in case you're interested in these topics. So we're going to cover these quickly and move on to the next lecture. Yeah, so I'll cover this slide before I forget. So this is an aside, again, this is phase change memory. It's a completely different technology than what we have seen before. You have a material, this is your storage node. How you store data is in this material, and it can exist in two states. What does that mean? It's either in an amorphous state, what we call an amorphous state that has high electrical resistivity, and a crystalline state that has low electrical resistivity. So how do you, okay, it's interesting how you program this more than how you read this out. So I'll start with programming. Basically, there's a heater element here that will produce some heat essentially in this this part that you see where the heater element contacts the material, the phase change material. If you heat this up and cool it down very fast, basically you heat it up to 600 Celsius and then suddenly cool it down, it will get into an amorphous state, the material you have there. If you heat it up to, let's say, 450 Celsius and slowly cool it down, it will go into a crystalline state. And the difference between those states allow you to encode data. So in the crystalline state, this material will conduct electricity better, like you will have more charge flowing through when you want to read this cell out. Whereas in the amorphous state, it will conduct electricity worse, so you will, based on the difference in conductivity, you can figure out what data you store. Okay, now I'll have this comparing DRAM to PCM, but I'll summarize this as there's no perfect memory. You can see some trade-offs here if you want to review the slide in the future. Not everything is green, basically that's the important takeaway. There's some things are red here. And it's interesting because you can decide to have PCM-based main memory. Its performance is somewhat closer to DRAM. Its cost is better, but read latency is a bit problematic. So you can decide different organizations for a PCM-based, well, when you want to use PCM as memory in your system. So these two papers that you see here have explored different sort of organizations that involve PCM. So you can have a PCM-only system. You can have PCM and DRAM in the same memory subsystem and figure out what, where to place data and which technology to access based on your workload characteristics. Or you can have just DRAM like what we have today. And this is an interesting research direction. I think it was an interesting research direction. And Professor Mutlu has this paper that basically is titled Architecting Phase Change Memory as a Scalable DRAM Alternative, where they explored the answers to these system organization questions. And this is the same, I guess, a similar version of the same paper. And interestingly, Intel had this technology, phase change memory. Well, I guess when Professor Mutlu described this slide, he says they don't explicitly mention this is phase change memory, but everyone knows that it is phase change memory. And there are basically real products. There were real products that had PCM that you could put in your where you put DRAM modules in your systems. But I guess it didn't work out, and Intel killed that line of product. Okay, so I'll skip these slides because we're running out of time. There are other promising resistive memory technologies. We talked about PCM. There's STT-MRAM, spin transfer torque, magnetic random access memory. I hope I got that right. You inject current to change magnetic polarity, magnet polarity. That's how you. That's closer to how hard disks work. It's not the same, but similar. There are also memristors. We looked at PCM a bit, and if you're interested in these emerging memory technologies or memory at all, I suggest you watch this lecture, or this one, and maybe I'll talk about flash just maybe a minute or two. When flash first appeared, it was a doubtful emerging technology for at least 2 decades. That's what the slide says. And we have, in our research group, we've done work characterizing flash memories as well to see how reliable they are, or well, how resistant to errors they are, let's say. And we built some infrastructure that allows us to test these flash memory-based SSD chips. And we have some lectures on this that talk about flash memory and SSD specifically as a memory technology or as a storage technology. And we also have courses where you get to do hands-on research or participate in hands-on research projects that concern SSDs. And here are some other pointers to you if you're interested in these topics. We talked about memory a lot, and one reason why memory is very important today is because you need to move data from your memory chip to your compute chip. We've talked about in the last lecture specialized data generators and general purpose data analyzers, right? It's similar when you consider memory in the context of any computing system. You have to bring data from a remote memory chip to your processor chip, compute, do some operations on it, and perhaps write it back. That consumes a lot of energy and takes a lot of time. And processing in memory is basically it's a research direction or maybe a new paradigm where you try to move your processing units, computation basically near memory. And there are some examples to it from industry as well. There are some products being developed. Unfortunately, I don't have slides to showcase those, but I think they will be showcased in other lectures. And if you're interested in this direction, this is a very good tutorial to watch. And this is a good paper to read that gives you an idea of how what the state of the art looks like. What the state of the art looks like in processing in memory. Okay, this is a past PIM course, and actually I'm done with that. So I'll take your questions in the remaining 2 minutes if you have any. Otherwise, we can take a break and be back here at past 15. Okay.
Okay. Let's get started, everybody. If you take your seats. Yeah, thank you very much. So in the second part of today's lecture, we will talk about memory robustness. We will focus on DRAM because it's the prevalent memory technology for our main memories. I'm Giray Alıkçı, this guy, and I'm also working with Professor Mutlu. Okay. So I'll start with the concept of robustness in terms of reliability, security, and safety. So a simple question is like, there's an ice bridge. How robust do you think it is? So it seems like a huge bridge that is built, constructed in a nice way. That actually suffers from some mistakes that happen in the engineering of it, or design, or maybe even in the construction methodology. That results in a collapse of this bridge shortly after it's actually fully constructed. So this is something that we do not want in our systems if our systems are robust. Another example, how secure these people are. So it seems like there's a steady state place over there. They're just having lunch or having some drinks, enjoying their time. But we need to care about preventing unforeseen consequences, right? So this is all about security, and you can also extend it to reliability and safety as well. So would you drive a car like this? So it seems like you have all the control surfaces. You have a rope to control the wheel. You have something here to hit the pedals, but there can be many things that can go wrong here, right? So you do not want to. You want to prevent such unforeseen consequences. So going back to our technology, we're going to talk about this phenomenon called RowHammer today. This is a phenomenon where one can predictably induce bit flips in commodity DRAM chips. And at the time of like 2014, when this phenomenon is shown, 80%, more than 80% of tested chips were vulnerable to this phenomenon. And this is the first example of how a simple hardware failure mechanism can be exploited, and it can cause a widespread system security issue. And you have posts like this: forget software, now hackers are exploiting physics. So I'll take a step back and talk about an early position paper that talks about the issues that might come up with memory scaling going forward. Here is, like Ataberk already covered the circuitry. I hope you're familiar with this. So you have capacitor, you have an access transistor here. This is a DRAM cell, and you store the charge in terms of capacitor. You store data as in terms of capacitor charge here, right? So your capacitor needs to be large enough so that you can reliably sense the charge here, and your access transistor should be strong. And it doesn't have to have it shouldn't have high leakage, so you should be able to store this charge for a long time here. And if you scale down this technology, if you scale down the size of this capacitor and transistor, then you might face some reliability issues. And here is a plot that's basically showing the relative server failure rates collected from all Facebook servers. This is from a paper in 2015 that shows that as you increase chip density, you basically have the same chip size and you put more bits into the chip. And as you move from 1 gigabit to 4 gigabit, your failure rate in the servers increase. This is an empirical observation in this paper. You can find more details in this paper. It shows us that there can be some reliability issues, safety issues in our systems as we scale down the memory technology. So we need to understand memory technology, its behavior more. So we need to test the real chips and understand how they behave under such certain conditions. Today, I will focus on this paper from ISCA 14 that's about RowHammer, Philippine bits in memory without accessing them. Which is a curious phenomenon. Okay, so this is a DRAM chip. So we have rows. DRAM cells are organized as in as rows here. And internally, we access them in a DRAM row granularity. Ataberk talked about row buffer hits, misses in the previous lecture, so you're familiar with this. So we want to access data here. We basically need to open this row by applying high voltage to a line called word line here. And then once we are done with this row, we need to close so that we can access other rows. And if we do this operation many times, like this, then we start seeing bit flips in the neighboring rows. And these neighboring rows can store your data or somebody else's data. And it's not good because you're not accessing them, but you're inducing bit flips there. So this is really like a reliability concern. So here we call the row that we keep activating and pre-charging or opening and closing hammered row, and the rows affected are victim rows. So repeatedly performing this operation can induce bit flips. And this paper shows that in 2014, it was like 10 years ago, more than 80% of the chips, tested chips, here you can see the percentages exactly, are vulnerable to this phenomenon, and they exhibit bit flips. And this paper shows that as you go from older chips to newer chips, so manufacturing data is on the x-axis from 2008 to 2014, you see that for some time you don't have any bit flips, and then first appearance is around like 2010, and then we start seeing bit flips all over the place. Why is this happening? Because of the increased DRAM chip density, cells are getting smaller and they are getting closer to each other. So when you access a DRAM cell, then your access, the electrical charge moving there, the voltage levels deviating, they cause interference on the other cells, and it leads to exacerbating the leakage and bit flips. So this has implications in several layers of the stack. So it's not just a physical phenomenon that happens in the bits and then stays there. You can actually exploit this in the higher levels of the hierarchy. You can affect the behavior of the operating system or the applications. And from the user level, you can just write a simple program like this in assembly. And you can actually perform this behavior. So let's say you somehow avoid cache hits and you avoid row hits as well. You end up accessing two rows back to back like this, and then it causes bit flips. And this paper shows that these real systems are vulnerable to this phenomenon, and they exhibit many errors. So this is the paper that is published in 2014. It's from Safari. And a follow-up paper from Google's Project Zero actually showed that you can actually reliably exploit this phenomenon in a real system, in a realistic scenario. You can induce bit flips in the page table entries, which actually is the key part of how we access memory, right? And you can actually leverage your privileges. You can get kernel privileges from a user level application. So this phenomenon is called DRAM RowHammer vulnerability. There are some fancy images, and in an analogy, it's explained like it's like breaking into an apartment by repeatedly slamming the neighbor's door until the vibrations go through and open the door you're after. It seems like super unrealistic when you explain like this, but there are many works in the field actually that shows that you can reliably exploit this phenomenon. For example, you can write a JavaScript code to exploit this phenomenon. You can use this in mobile devices. You can use GPUs to efficiently conduct or mount your attacks. You can use network packets to attack some remote machines in different ways, basically. And you can also use FPGAs to accelerate this attack. You can use this attack to take over a system or simply leak some critical information from a system as well. You can attack to some neural nets that are running on some systems. For example, in a self-driving car, if you can mount this attack, you can change the behavior of the neural net over there, and you can reduce the accuracy from 90% to 10%, meaning that the car will crash, right? So it's quite important. And there are many works like this. You can use this as a side channel as well. So there are many security implications, and this list can go on and on. But I'm just giving some examples. So if you're curious about the implications of this, there's a retrospective paper that was published in 2019 that covers like the immediate impacts of this Philippine-Bits paper from 2014. You can take a look at that. And there are more up-to-date versions of this retrospective as well, which is here, that was published last year in ASP.DAC in 2023. Okay, so let's understand RowHammer a little bit more. So let's dive into this paper that was published in 2014. In this paper, they used this infrastructure where you have a host machine and a FPGA, and DRAM is plugged into this FPGA. And there's a heat chamber that the DRAM chip sits in, and there's the heater that heats up this chamber, basically. And there's a temperature controller that measures the temperature inside and turns on and off the heater. So you, so you can have a stable environmental conditions for this DRAM chip to test here. This is a flexible infrastructure. We have a custom design inside the FPGA that allows us to issue DRAM commands precisely and timely. And it has a very easy to use C++ API, and it's open source on this address. But don't go to this address. I'm going to show you another address sometime soon. That is actually an updated version of this that has more capabilities. Yeah, this is just the reference for the infrastructure. And this is the updated version of that infrastructure that today actually supports like many different boards. And it supports DDR3, DDR4, and LPDDR, well, not LPDDR4, but DDR3 and DDR4 DRAM modules. Also HBM now that we can give you access to some HBM version of that as well if you're interested. Okay, this is another picture of the same setup with like multiple boards here. So we parallelized our test. We test many modules here. So there's like 129 different modules that has like many chips basically. And we show that most modules are at risk. And you either use old chips that are smaller in capacity and slower chips, or you need to bear with these errors. And these errors are related to the charge loss, and it has this property of adjacency. Basically, you observe the bit flips in physically nearby locations of the addresses that you access. And there are more sensitivity studies and other results, and there's the exploration of the solution space as well. So here's an example of one of those results. So about the adjacency. So here on the x-axis, we have the row address difference. This is a relative row address. Basically, we keep, I'm not sure if you're seeing my laser pointer. Maybe I should use this cursor here. So our aggressive row is here in the location 0. And on the y-axis, we see the bit flips, number of bit flips, right? So most of them are accumulated in the immediate adjacent rows. And there are some rows that, bit flips happen in some other places as well, in non-adjacent places. Yeah. So if you look at the access interval, it's actually quite straightforward that if you access the aggressive row very frequently, then you have more bit flips. If you access them less frequently, then you have less bit flips. And the 55 nanoseconds is just like the boundary that is mandated, forced by the specification. You cannot access more frequently than this. Okay, so if you have less frequent accesses, you have fewer errors. If you refresh more frequently, you can prevent errors. If you refresh less frequently, then you have more errors. Quite intuitive, right? So this actually leads us to the mitigation method. So how can you avoid such bit flips? If you refresh those potential victim rows frequently, then you can avoid such bit flips. But you need to refresh rows like 7 times more frequent, right? Based on this result. And it's even worse today. So it's not really like a viable option to refresh all rows very frequently. Okay, there's some sensitivity to the data pattern. I'm not going to go into that. And I'm not going to go into those other results as well, but you can check them in the paper if you're interested. And there's a follow-up paper of that I will explain later in the lecture. Like many follow-ups, actually. So we will go through this one by one. Okay, so this paper in 2014, after showing this vulnerability, this phenomenon, it actually suggests immediate and long-term solutions. Immediate solutions are the solutions that you can deploy immediately, basically some software updates. And longer-term solutions require changes in the hardware, either in the DRAM chip or in the memory controller. And you can summarize those longer-term solutions, well, actually some of the short-term solutions as well, into like these categories. So you can come up with more robust DRAM chips, of course. You can have more sophisticated error correcting codes. You can increase the refresh rate to some extent. You can provide some physical isolation between the attackers and victims' data. You can refresh rows based on some access patterns, which is called reactive or preventive refresh, or you can choose to throttle or slow down the memory accesses. And all of them have different trade-offs of cost, power, performance, and complexity. Apple went ahead with some software update that actually increases the refresh rate to mitigate such errors, but it's not viable today. So the solution proposed in the paper is called PARA, probabilistic adjusted row activation. So basically, whenever a row is activated, with a low probability, you refresh the rows adjusted to that. How do you do that? You generate a random number, you check, compare that random number to a threshold, which is 0.005 here, and you basically perform the preventive refresh. So it refreshes rows infrequently, so it doesn't have super large performance. Sorry, go ahead. I couldn't understand. Could you repeat? So of course, when you have, the question is like, does ECC RAMs, do ECC RAMs also affected, right? So yes, they are affected. This is a circuit level phenomenon. It happens to them as well. If you have error correction capability, then you can correct part of the errors, but it doesn't guarantee that you can correct all the errors, right? If your bit error rate is above some level, then you cannot actually protect it. I will show some results as well. Basically, some data from 2021 shows that in a 64-bit data world, you can have more than 7-bit flips, which is too much for the current ECCs deployed in today's systems. So they are also vulnerable to this. Is that okay? Good. Okay. I'm not going to go through the requirements, but you can see PARA implemented in real life. This is a screenshot from a BIOS, well, more of a picture actually, that you can actually enable on some systems this probabilistic row refresh, and you can also play with the thresholds based on your DRAM chip's vulnerability level. So this is the Philippine Bits paper from 2014. And it shows that main memory needs more intelligent controllers to ensure robustness and scaling. This requires understanding the underlying phenomenon more, of course. And this is similar to how we control NAND flash as well, which is also an unreliable memory, as Ataberk mentioned in the previous lecture. So we have more intelligent controllers over there, right? And we have some similar error characteristics as well that is shown in this paper. So we need some similar intelligent controllers for those. You can see these retrospective papers. But going forward, we need to invest more on understanding RowHammer better and solving RowHammer. So, so far, are there any questions? No, okay. So I have 25 minutes and I have around like 100 slides. Let's speed run a little bit. So you don't have to remember any of these details anyway. Okay, so let's look into what industry did for tackling this problem. So for a while, in mid-2010s, actually, if you look at like posts from that time, you can see that some manufacturers claim that they have RowHammer-free DRAM chips already in the market, and they say that it's not really a concern anymore. And they deployed some mechanism called target row refresh, which is in short TRR, that solves the problem. And so this paper challenged that. So this is a paper that was published in IEEE SMP in 2020 that shows that TRR-protected DRAM chips are vulnerable to RowHammer. So even though there's protection, and you verify that there's protection, you can actually play with the access patterns. You can be a bit more smart from the attacker's side, and you can induce bit flips. And how do you do that? They introduce many-sided RowHammer attack, where they hammer not just 2 rows, but multiple rows. And it is enough for bypassing basically the deployed mechanisms of that time. And this is how it looks like. So the red rows here are the aggressors.
Could you explain again what like hammering the rows means?
Sure. So you basically, do I have another animation? Maybe I can explain on this figure. So, sorry. So this red row is one of your aggressor rows. This red is another aggressor rows. You basically open and close them many times. And once you open close them many times, it affects the leakage in the row in between. Excuse me. And the row in between, which is victim row, experiences bit flips as a result of this, like opening and closing many times. And what they do here is that in this 4-sided version, for example, they put like they assign 4 rows as their aggressor rows that are like 2 rows ahead from each other. And then they hammer them simultaneously, well, concurrently. And then this is enough for bypassing the deployed mechanisms and inducing bit flips. In these plots, it's shown that like as you increase your number of aggressor rows, you can actually have bit flips. So for up to 4 rows, for example, if you hammer just 4 rows, your mitigation mechanism is effective. You do not have bit flips. But at 5 rows, for example, on that plot, you see a lot of bit flips all of a sudden. And they test many chips from 3 major manufacturers that is covering like more than 99% of the market share. And they show that pretty much all of them are vulnerable. And they also test this on some mobile phones. And then they show that they can actually have bit flips on these like tilt ones. Yeah. And these are the, so for stealing your RSA key, for example, they only need like 6 minutes of this attack, or to polluting or like modifying your page table entries, it's very quick, like in 5 seconds, they can have root privileges, for example. So you basically go, so you only flip bits, yes, but those bits have meanings in the system level. For example, it tells you if you have permission, write permission on some page table entry. So if you guide it that way, it's this PTE actually. In 5 seconds, you can get the root access. Well, for sudo, it's like 54 minutes here. Anyway. So basically, it's showing that the chips that are marketed as RowHammer safe are not actually RowHammer safe. Okay, So it tells us that RowHammer is still an open problem, and security by obscurity, basically they say that they solve it, but they do not explicitly mention how they solve it. It's not a good solution. So there are several sensitivities of this phenomenon. One of them is data pattern. So usually you put your data pattern in your aggressor row in such a way that you can guide where the bit flip will occur. It's not guaranteed, of course, because it's some unreliable behavior in the system anyway, right? But if you insist a lot and if you put a lot of effort, you can actually do that. When you hammer the adjacent rows to flip that bit, I'm assuming you don't hammer two rows, you have to work throughout a bunch of stuff. How do you make sure you don't just completely break the system? Because when you hammer, when you hammer the rows, do the bits flip on that row? No. Oh, wait. So the first thing you said is correct, actually. There's a chance that you can also have bit flips in the places that you do not want, and it can crash the system as well. So it's not guaranteed that you will be always successful in the way that you want. You can crash a system as well. But there are some examples that show that you can reliably do some sort of attacks under some conditions. And there's an ongoing research on this. Like every new attack becomes more reliable. For system level attacks, for this kind of questions, if you're interested, I would suggest Kaverezavi's lecture as well, if you're familiar with him. You can actually get some hands-on system level attacks over there. For us, you can also play with the DRAM chips if you're interested. Okay, so another paper that is follow-up of the paper that I just described, that's published in Micro 2021, dives more into how these mechanisms work. It reverse engineers these mechanisms by leveraging their data retention time characteristics. And it shows that in 99.9% of the rows that are tested, at least one RowHammer bit flip is observed. And if you look at the 8-byte data words, you can have more than 7 bit flips when there is the TRR protection mechanism. So it tells that TRR does not provide security, and ECC is not enough, and we need better solutions. So there are many chips tested in this work as well. You can find more details in the full paper. Following this, there's another paper that came from Google that's called half double, a new kind of attack, basically. What it does is now you play with your aggressors, how you access your aggressors a little bit more. So you concentrate most of your activations in a far aggressor. So this is your victim. This is called the near aggressor, basically the one adjacent to the victim. And there is a bit farther aggressor row. And you concentrate most of your activations here that causes refresh operations that happen on this aggressor and this aggressor. And you also activate this aggressor a little bit more. And then you have bit flips in here. And this is a way of basically bypassing the deployed TRR mechanisms again. And it's also published in Usenix Security in 2022. So, so far, are there questions? Yeah.
Do you need to have physical access to the system where you want to keep the bits, or can you do it somehow?
In some attacks, yes, you need physical access, but there are also attacks. I show some examples like NetHammer, RowHammer. You can search for those papers. They actually use network packets to access the remote memory. So you have this direct memory access module in your architecture, right? You can, from the network chip, you can directly access there and access the memory. And you can use that for mounting attack, yeah.
With virtual memory addresses, how can you ensure that you actually target the right row?
Yeah, there are many reverse engineering steps involved in there. You basically, so the most practical way of doing that is allocating some huge pages. And it actually already guarantees you that you have some consecutive physical address space, and you can access like different rows over there. But even if you don't have huge pages, there are some works in the literature that tells you how you can force the system to allocate the data that you're attacking in a certain physical location. You basically like allocate a lot of memory address space, and you leave like a little bit of that for that data that you're after to be allocated there.
You mean that you could protect certain very specific addresses by allocating space to the side of them?
Yes, you can do that. There are works that suggest that as well. But if you have sensitive data, only like a little piece in your system, that can be feasible. But if you do not want your system to crash, for example, then you need to protect like pretty much every data stored in there, right? So you need to allocate a lot of space. So it actually goes backwards. Now you lose a lot of your capacity just for like isolation between rows. And you can just like go back and use DDR2, for example, instead of DDR5 now. Yeah. Other things? Other questions? No? Okay. So I said that with technology node scaling, DRAM cells get smaller and get closer to each other. And as a result, now we can achieve bit flips like 2 orders of magnitude smaller hammer counts compared to 10 years ago. So it means that we are much, much more vulnerable today in the circuit level. So this Revisiting RowHammer paper tests like 1,500 different DRAM chips and shows that only like 4.8K of activations are enough for inducing bit flips. And when you look at the chips from the same protocol, like for DDR3, for example, I show here. For DDR4, for example, if you look at old chips and new chips, you can see that there's a significant reduction in the minimum hammer count needed to induce the first bit flip. So it's much easier today, actually, to achieve these bit flips compared to 10 years ago. Okay, and as a result of that, now your deployed protection mechanisms need to be more aggressive. They need to refresh rows more frequently, and it induces significant performance overheads. And that's the main concern nowadays, actually, not the reliability or security, because if you're aggressive enough, you can ensure robustness, but it comes at the cost of losing your performance, losing your availability, losing your fairness. And this is a more more of today's research problem. Okay, I will just go through I will just skip these slides because I want to focus on some other things in the remaining time. But we looked at some different sensitivities of RowHammer in the past years. You can, so you have the slides in the website anyway. You can go to this video, and I talk about all of them over there for like 2 hours. You can listen to them if you're curious. So the question is, are we now RowHammer free in 2023? The obvious answer is no. There is actually an important paper that was published last year in ISCA that's called RowPress that shows yet another redisturbance phenomenon other than RowHammer. So this is the access pattern of a RowHammer attack. You open and close rows as frequently as possible. So what this work does is that let me just wait a little bit, take my time when I open a row, let the row stay open for some longer time, and then close it. And this has a huge impact. So if you wait like 36 nanoseconds when you open a row, you need 47,000 activations to induce a bit flip. If you keep it open for 7.8 microseconds, then you have bit flips at 5,000 activations, an order of magnitude reduction here. And if you wait long enough, only one activation is enough to induce a bit flip. So there is a rigorous experimental analysis in this paper. They test a lot of chips and show that RowPress significantly implies DRAM vulnerable to read disturbance, and it's a different underlying mechanism than RowHammer. So they can work together actually in the attacker's benefit, basically. Okay, I'm gonna skip these. There's a real system demonstration as well. Ataberk here did it, so you can ask him the questions, but there's a snippet of code here that actually helps you induce and raw press bit flips on DDR4, a real DDR4 machine. And you see that in this machine, you cannot induce bit flips by doing RowHammer attack, but by doing raw press, you can have bit flips. Okay. Let's skip this and skip this one as well. Are you familiar with HBM chips? Ataberk talked about the 3D DRAM arrays in the previous lecture. So this is another way of doing the 3D arrays that is widely used today actually in the FPGAs and in some processors and GPUs that are used for like accelerating modern workloads, right? So like with LLMs, for example, you would use HBM chips. And there's an analysis of that. It's vulnerable to RowHammer, raw press as well. This is a short paper, but a longer version is coming up this June. Okay. So we also suggested proposed some solutions as Safari in the field. So we propose like let's slow down some accesses, for example, in this paper. This paper parallelizes the refresh operations to reduce their performance overhead. This paper looks at the heterogeneity in the vulnerability of different DRAM cells in a DRAM chip and leverages that. So we also have another talk that covers all these. I'm just going to show that and then leave it. We have some upcoming papers, such as this one, that actually proposes a way of dealing with the metadata in a more efficient way. This is also recently published work that is targeting the same thing. And with that, I'm just gonna leave the solutions over there. In the last 8 minutes, I will focus on the RowHammer works in the field, other than like what we do since 2020 until today. So I'm not gonna get into details of these papers, but I just like collected pretty much a comprehensive list of the recent publications in the last 4 years, which is basically many. The takeaway here is like there are many works, and in major conferences there are even sessions that are dedicated to RowHammer. So it's a quite relevant research field today. So if you're interested, and if you have ideas, you don't have to have ideas at the moment, of course. You can work with us to build on this research. Yeah, I just wanted to highlight the slide actually. This is one of the major security venues using Security Symposium. And there are like 4 papers accepted that are relevant to RowHammer, and 2 of them are from ETH, as you can see. So you're at a good place to work on RowHammer and related topics if you want to. Okay, let's look at some industrial solutions in the last 7 minutes from 2020. So after we showed actually that the deployed mechanisms are not providing the robustness that we want, there are more attempts from the industry to solve this problem. So weirdly, this paper came out from Microsoft, which is not a hardware company, and a small company called Avantgrey that is proposing to put some activation counters inside the DRAM array so that we can accurately identify which rows are being accessed frequently and perform refreshes to them. So this is a very short paper, easy to read, and you can find a lot of resources about that. There's a link here as well. You can check it. So this was published in 2021 in a small workshop called DRAMSec. And then in 2023, we had the first paper from a DRAM manufacturer, ST Hynix, that is showing some similar proposal that dedicates a counter per row inside the DRAM chip and detects RowHammer in that way. There's another paper similar from Samsung. And this is a very recent advancement in this problem. This is like less than a month old, basically. There is a new DDR5 update that proposes implementing per-row activation counters inside the DRAM chip. And DRAM chip has a new signal that is called a backoff signal that DRAM chip sends from DRAM chip to the memory controller, saying that I need some time off so that I can perform some preventive refreshes to avoid RowHammer bit flips. And the memory controller allows the DRAM chip to perform those preventive refreshes. So this is something quite new. And there is a blog post that explains this from the author of the Panopticon, actually. And it's very nice to see that there's a reference to Professor Mutlu's lectures as well. So from this blog post. If you're curious, you can follow those lectures as well. And we are open for like collaboration. You can work with us. So are we now RowHammer free in 2024 with these updates? Any guesses? Another paper that is published, that will appear in User Security in this August from Kaverezavi's group that shows that even in DDR5 chips today, you can actually achieve RowHammer bit flips. So we need better RowHammer solutions. We need more intelligent controllers for robustness and scaling. And there are many trade-offs from different approaches. And we need to exhaust the search space, and we need to find better solutions. We have the necessary tools to conduct this research. This is a DRAM timing simulator that actually you can use. It's an open source one to try out your ideas. We have an FPGA-based exploration of DRAM and RowHammer PNS course. But you don't have to enroll for this PNS course, of course, to work with us. You can just come and work with us. But you can get benefits of the resources in this course webpage. And we have an upcoming summer school in early June that will happen here. So if you're curious about this computer architecture topics, reliability topics, RowHammer, you're welcome to follow these lectures. Probably they will be on YouTube anyway. But yeah, I wanted to encourage you all. And with this, I'm done with my lecture. So we have 3 more minutes if you have any further questions. Yeah. Today it's a bit harder because of all the mitigations. But if you want to get your hands on, just like come to us, we can guide you to conduct achieve bit flips basically by doing system level attacks. It's still possible. It's not very easy, but it's still possible. If there's no other questions, we can conclude the lecture. Thank you very much.